All right, this is Unit 2 review number 3, the AP Classroom Progress Check, Unit 2 Progress Check MCQ Part B. We'll go ahead and go over that. This is my first time seeing these problems, so I might have to pause and kind of work things out before I explain them. You should try these problems on your own too before you check my video. So if you haven't done that yet, pause, come back to the video when you get a chance to work them out. All right, progress check number Unit 2, Part B. Give it a second to load. Let's see if we can find it. Progress check. Unit 2 progress check Part B. And pretty slow today. All right, here it is. So question number 1. A small business owner has created a linear regression model to predict the number of new customers who will visit a shop based on the number of times the owner has an advertisement played on the radio. What's the explanatory variable and what is the response variable? So you're predicting the number of new customers, so that's going to be the explanatory, that's going to be the response, is the number of new customers. So the explanatory would be based off of number of times the owner has an advertisement on the radio. So the advertisements predict the number of customers. So it would be this one, number of times the advertisement is played versus the response variable, number of new customers. Number 2. Bankers at a large financial institution created a linear regression model, D hat equals 0.37 minus 0.0004S, to predict the proportion of customers who would default on their loans, D, based on the credit score, S. For a customer with a credit score of 700, what's true? Well, let's plug that in. I'm going to pause that in video and plug it in. Okay, when I plug in 700, I get 0.09. Now, we have two ones with 0.09. The default proportion is predicted to be 0.09, or the default proportion will be 0.09. And you should know it's predicted because we don't know the exact number. All right, number 3. Marketing consultant Sophia has been studying the effect of increasing advertising spending on product sales. Sophia conducts several experiments, each time spending less than $1,000 in advertising. When she analyzed the relationship between X equals advertising spending and Y equals product sales, the relationship was linear with R equals 0.9. Her boss is thrilled and asks her to estimate product sales for $100,000 in advertising spending. Is it appropriate for her to calculate a predicted amount of product sales with advertising spending of $100,000? Okay, so when we're looking at this problem, one thing stands out. I had to reread it. She's doing numbers with less than $1,000. So she's doing all these predictions, $1,000 here. And then she wants to go ahead and predict amounts with $100,000. So 1,000, 2,000, 3, we're talking way out here. And no, we don't want to make predictions. That's called extrapolation. And that's generally not favored. So that's way outside of the values in here. So it's going to be no, because $100,000 is much greater than the values used in the experiment. All right, number 4. A researcher studying koi fish collected data on 3 variables, A, B, and C. The following residual plots show the residual for a model predicting each variable from the age of the fish. Random scatter variable A, variable B has kind of a U shape going on, and variable C looks like it has some sort of positive shape going from negative to positive. These are residual plots, mind you. A conclusion that a linear model between the variable and age is appropriate is supported by which of the plots? So I would say only A in this case, because B has a pattern and C has a pattern as well. You know, it's going from negative to positive and it's not randomly scattered. So really only A is randomly scattered. So we want to pick that one. All right, question 5. A marketing consultant created a linear regression model to predict the number of units sold by a client based on the amount of money spent on marketing by the client. Which of the following is the best graphic to use to evaluate the appropriateness of the model? Well, that's going to be a residual plot. We're in unit 3. We're unit 2. We're in scatter plots. A residual plot will tell you if a linear regression is appropriate or not. So that's right there what we want to use. That's 2 variables. These are 1 variable data. So this is 2. All right, number 6. The following is a residual plot from a regression of a variable with an independent variable x. Based on the plot, is it reasonable to conclude that a linear model is appropriate? And the way I'm looking at that plot, I see a lot of no clear pattern, a lot of scatter randomly. And so I'm going to say yes, because the plots show no apparent pattern. That's what we're looking for a linear. No apparent pattern. That's a good thing. That's linear. All right, number 7. A grocery store wants to examine the relationship between the sales amounts each day at 2 different locations, store A and store B. Sales amounts each day in dollars was recorded for 10 days at each store. The least squares regression line is y hat equals negative 3,000 plus 1.2x, where x represents the sales amount each day at store A and y represents the sales amounts each day at store B. If the mean of the 10 sales amounts for store B is $45,000, what's the mean of the 10 sales amounts for store A? I mean, you got to know this. You got to know that the mean goes through the point. That goes through the scatter plot. That line of best fit, least squares residual, least squares regression line. I can't talk. So if the mean of the 10 sales for store B is 15,000, X represents the sales for store A, so this really is the Y mean. So 45,000. And we got negative 3,000 plus 1.2 times what's store A? That's the X mean. This is algebra. Add 3,000 and divide by 1.2. Take a moment to try that. Make sure you can get the right answer. And that's going to give you 48,000 because we got to add that 3,000. And 48,000 divided by 1.2, I don't know what that is. $40,000. Okay, question 8. The least squares regression model y hat equals negative 3.4 plus 5.2x, and the correlation coefficient r equals 0.66 were calculated for a set of bivariate data, 2 variables, with variables x and y. Which of the following is closest to the proportion of the variation in y that cannot be explained by the explanatory variable? This is proportion of the variation in y that can't be explained by x. That's r squared. That's called the coefficient of the termination. Well, if I have r as 0.66, I can certainly just square that and see what that is. So let's put that in the calculator. And 0.4356 is your r squared, 0.4356. So that means 43.56 of the variation in y could be explained by x. Not too good, but again, that'll be your 44 as your closest number there. All right, next question. Number 9. A botanist created a linear model to predict plant height from soil acidity for a certain type of plant. The slope of the model was 2.5 centimeters per pH level. The standard deviation of the sample of plant heights was 4 centimeters. And the standard deviation of the soil acidities was 1 pH level. What is the value of the correlation coefficient? This is the formula you need. See, I told you you're gonna have to use that formula. So we're given the slope, there's your B. What is the value of the correlation coefficient? So we don't know that. But we do know standard deviation of the sample plant heights was 4 centimeters. And we're predicting the plant height. So that's gonna be your Y, so 4. And standard deviation of soil acidities, that's going to be your X, so that's going to be 1. And so 2.5 equals 4 times R's. So 2.5 divided by 4 equals R. And so that's going to be, well, let's see, that's going to be 5 out of 8. So that should give you 0.625. That's your R value. All right, we're halfway through. Number 10, let's go. All right, in baseball, 2 statistics, the ERA, earned run average, and the WHIP, walks and hits per inning pitched, I've never heard that, are used to measure the quality of pitchers. For both measures, smaller values indicate higher quality. The following computer output gives the results for predicting ERA using WHIP, and NANE, and a least squares regression in the 2017 baseball season. If you're listening to this video and you heard me mention that to me, I want to know if you actually paid attention. Okay, which of the following statements is the best interpretation of the value of 6.8 in the output? Well, you're not going to need to know what that is yet, or that, or that. What we need to know for the intercept and the slope, this is your A, this is your B. Intercept, slope, 6.8 is the slope. So that's what that is. So ERA is predicted to increase by 6.8 units for each 1 unit increase of WHIP. Well, what's the X value? 2 statistics, ERA, earned run average, and the WHIP are used to measure quality of pitches. For both measures, smaller values indicate higher quality. We're predicting ERA by using the WHIP. So WHIP is your X, ERA is your Y. WHIP is your X, ERA is your Y. So for each 1 unit increase of the WHIP, we would expect our ERA to be increased by 6.8 units. That's your answer. ERA is going to increase by 6.8 units for each 1 unit increase of WHIP. Remember, slope is when you increase X 1 time, that slope value is what Y increases by or decreases. All right, number 11. Jordan is working on a business model for a sandwich shop. Based on the past data, he developed a model, n hat equals 150 minus 3p, where n hat represents the predicted number of turkey sandwiches sold in 1 day for a price of p dollars per sandwich. Which of the following is the best description of the slope of the model? Well, it's negative, so it's going to go down. So for each increase of p, we would expect n to go down by 3. So let's see if we can analyze that. For each increase of, it's always an increase of $1 or 1, not 3. So for each increase of 1, the price of the sandwich, the number sold is predicted to decrease on average by 3. And that's really what we're looking for. It's decreasing by 3 for each increase of 1 X value. So as X increases by 1, Y decreases by 3. All right, number 12, we're getting there. It's a long problem, long set of problems. Appreciate you hanging in there. Also, my favorite color is blue, mention that. Researchers are investigating how the amount of monthly rainfall measured in centimeters affects the monthly growth in centimeters of a certain plant. For a sample set of data, the researchers created a least squares regression line. Computer output is shown in the following table. Ignore that, ignore that, ignore that. There's your A, and there's your B. All right, which of the following statements is an interpretation of the value 0.75? That's your intercept. So remember, intercept is when slope is, or when x is 0, what's the y value? So monthly growth is expected by increase by 0.75 when rainfall increases by 1. No, that's slope interpretation. Rainfall is expected to increase by 0.75. No. For a month with 0 centimeters of rainfall, the monthly growth is expected to be approximately 0.75 centimeters. For a plant with 0 centimeters of monthly growth, the month had an expected rainfall of 0.75. So for example, let's see, we're predicting the growth. We're predicting growth. That's your y. And rainfall is going to be your x. So it would make sense for x to be, in that case, for a month with 0 centimeters of rainfall, the monthly growth is expected to be approximately 0.75 centimeters. That's your baseline. That's how much it's going to grow without rain. All right, next question. The following scatter plot shows a company's monthly sales in thousands of dollars versus monthly advertising dollars spent in thousands of dollars. There's that growth. Which of the following points is most likely a high leverage point with respect to a regression of monthly sales versus advertising dollars? So high leverage point would be something out here, but in the positive direction up here, strengthening that correlation. So if we look over here, 5.1 and 105, I would say that's not a high leverage point. All right, I had to reread that because when I'm looking at these points here, it's asking for one of these points to be a high leverage point, and I'm not seeing any of these points as being high leverage because they're all kind of close together. But a high leverage doesn't necessarily have to have a high X value. It just has to be far away from the other points, but strengthening the data, strengthening that correlation. So actually this 5.1 here is considered a high leverage point because if I were to remove that, that would change the way that this linear regression would be. So 5.1105 is our high leverage point, even though it's lower, like, you know, to the left and down, it's still in the general direction of that line. So it's extreme value, high leverage point. Hope that makes sense. All right, number 14. The following scatter plot shows 2 variables along with a least squares regression line. Which of the following points is an outlier for the data? Well, you know, it's pretty obvious to me that this point right here is an outlier. So that would be 5,24. So if you, yeah, that's 524, that's an outlier. Everything else is pretty close to the line. All right, number 15. Following scatter plot shows the ages and years of 12 of the wealthiest people in the world along with their net worth in billions of dollars. The data point at age 83 is labeled Q. All right, suppose Q is removed. Which of the following is likely not affected by the removal? Correlation coefficient would be affected because that's an outlier. So that's going to change the R value if I take that out. The sign of the slope of the coefficient. So I'd say that slope would be positive, and it would still be positive, but it would just be steeper, so that's not true. The value of the slope will change. Oh, so the question is, which of the following is likely not affected by the removal? The sign of the slope will still be positive regardless. The sum of the squares residuals will change. It'll be smaller because you don't have the outlier. And the net worth intercept. The intercept will change because it'll probably go from down here to maybe over here. So it'll be a little bit higher there. But the sign of the slope, that's not going to change. It's still going to be positive. All right, question 16. A real estate agent wants to predict the selling price of a single-family homes from the size of each house. A scatter plot created from a sample of houses shows an exponential relationship between price in thousands of dollars and size in 100 square feet. To create a linear model, the natural logarithm of price was taken and the least squares regression line was given. ln of price equals 2.08 plus 0.11 times the size. Based on the model, which of the following is closest to predicted selling price for a house with a size of 3,200 square feet? So we're going to use our calculator here, and we're going to plug in 3,200 into our equation. Now it's talking about ln here. ln, that base is going to be e. So we're going to do second ln right there. And we're going to raise that number. And, whoa. All right, well, clearly that's going to be too much, and I misread that problem. It says size in 100 square feet, so this would be 3,200, so 32 would be your input there. So well, let's try that one more time. 2.08 plus 0.11 times 32 in 100 square feet, so that's 5.6. And now do second ln, and then 5.6 and 270, and this is in thousands of dollars, so $270,000 would be your answer for that one. Keep up with those units. They can get you sometimes. They almost got me there. Question 17. Workers at a warehouse of consumer goods gather items to the warehouse to fill customer orders. The number of items in a sample orders and the time in minutes it took the workers to gather the items was recorded. The scatter plot of the recorded data showed a curved pattern, and the square root of the number of items was taken to create a linear pattern. The following table shows computer output from the least squares regression analysis to created to predict the time it takes to gather items from the number of items in an order. Based on the regression output, which of the following is the predicted time in minutes that it took to gather the items if the order has 22 items? So let's try this again. We got our intercept and our slope. Let's write this down. We got 3.0979 plus 2.7633, and we're square rooting the items here. So we have 22 items. Square root of items is not just x, it's the square root of x. So 3.0979 plus 2.7633 times the square root of 22. Of course, that's going to be a decimal of sorts, but let's see if we can calculate that. And we're talking about 16.058, so 16.06 minutes. And one more question, if my computer will let me. It's being kind of slow. I think that's a sign of me I need to turn it off. A new town was incorporated in 1960. The size of the town's population was recorded every 5 years after 1960, using the variables x for number of years since 1960 and y for the size of the population. 3 models were created to predict the population for the number of years since 1960. Boy, they like to repeat themselves. All right, model 1 predicts y from z. That's model 1. Model 2 predicts ln of y, the natural logarithm, from x, so ln y from x. And model 3 predicts ln y from ln. This is linear, exponential, and power. And the question says, which of the following is the best interpretation of the residual plots? Well, let's take a look. Linear model is not so good because it gives you a pattern. This is the exponential. This is the second one, ln y from x. Pretty random scatter. The third one has seemingly a pattern again. That's ln y, ln x. So the middle one is the one we want. The residual plot for model 1 indicates the quadratic model is the most appropriate among the 3 models. That's not necessarily true. That's just the pattern here for the residual plot when you do a linear regression. The residual plot for models 1 and 3 indicate that either model is appropriate and better than model 2. Like I said, I like model 2. The residual plot for model 2 indicates that it is the most appropriate among the 3 models. D, all the residual plots indicate that any of the 3 models are appropriate for the prediction. And then E, all the residual plots indicate that none of the 3 models are appropriate. Like I said before, I like model 2 because it gives me a random scatter. That seems like that model will be the best appropriate for this situation here. So it's going to be C. So that is question 1 through 18. And I hope that was helpful for you. And you have a good day.